Right. So we finish off by writing off the relationship from bending from shear distributed load distribution, and then we got into our slope now, our deflection. Okay. So interest not a thing to take note is this. Okay. Now we have four constant. Okay, we have four constant to determine. So which is our C1, C2, C3, and C4. So therefore, we usually four boundary conditions are required. Okay. So four boundary conditions are required for four constant to be determined. Okay. So take note of that. Okay. So you need to determine four unique. Okay. I repeat again, four unique boundary conditions. Okay. So let's look at an example on this approach. Okay. Let's look at an example. So this example, I'm going to change a page for you guys. Hold on. Okay, so let's look at this example. So I think this is our I could not remember how many questions we've done already. Hold on. One. Then we have done. Okay, we only have done one. So this is our example number 2. Okay. So by looking at example number 2, again, example number 2, I'm going to have it. Now I'm going to make it simply supported beam. Okay. And this simply supported beam has a gradient, okay, a easy gradient. So over here, this is our omega naught. Okay, so we're going to find. Okay, this question requires us to find. Okay, we're going to find the deflection equation of the beam. Okay, again, I'm going to show you two separate methods. This one you can use okay, I'm going to show you two separate methods. Okay, so the first method, we're going to use what we learned today regarding integration method. Okay, so this method is just pure. So number one, just using integration. I'll put on the side. Number one, just using integration method. Okay, I'm not going to do left to right. Okay, just purely going to use integration method. Okay, so for the first thing we have to do, so we have to know that our boundary condition. So this is x equal to 0, x is equal to L. Okay, so this is our point A and our point B. So V M theta y, okay, V M theta y. And at point A, when x is equal to 0, M is equal to 0, y is also equal to 0. And x is equal to L, M is equal to 0, y is also equal to 0. Okay. So the first thing we have to do, as I said, we have to find the equation of the distributed line. Okay. So we have to find equation of the distributed load, right? So it's omega as a function of x, okay? The change in height is omega naught, and then the x-axis is L as a function of x. That's it, positive slope, okay? So that's, then we're going to apply dv by dx. Is equal to minus omega as a function of x. Okay, so it's equal to minus omega naught, okay, x. Okay, then we integrate. So when we integrate, it will be v as a function of x is equal to minus omega naught x squared over 2l plus by c1. Okay, so this is my equation number, and then this will be equal to dm by dx. Oops, okay, I got it. Sorry. Right? dm by dx. And this is our equation number 1. Right? Okay. So the thing now, do we have any boundary conditions to find C1? The answer is no. Okay. We don't know what our V are at x is equal to 0. X is equal to what? L. If that's the case, move on. We integrate again. Okay. So M, right? M as a function of x is equal to minus omega naught x cubed over 6L plus by C1x plus by C2. This is our equation number 2. So now our moment equation, which is equation number 2, we know our boundary condition for the moments. Okay. So what do I mean by that? We know when x is equal to 0, m is equal to 0. Right? We're going to substitute into equation number 2. So we're going to substitute. We're going to substitute when x is equal to 0, moment is equal to 0 into equation number 2. What we get is therefore C2 is equal to what? 0. Okay. So when that's the case, we again write down m as a function of x will be equal to minus omega naught x cubed over 6L plus by C1x, and this is your equation 2a. Okay, that's your equation 2a. Then from here, right? From equation 2a, we can substitute our next boundary condition. Right? So we know that our next boundary condition, we're going to substitute when x is equal to L, m is equal to 0, and then we're going to substitute into equation 2a. Okay, so this will be equal to 0, and this will be equal to minus omega naught L squared over 6 plus by C1L. So C1, right, is equal to omega naught L over 6. That is our C1. Okay. So therefore, we can now write down therefore m as a function of x is equal to minus omega naught x cubed over 6L plus by omega naught L x divided by 6. Okay, we can write that down there. Then from here, this whole equation over here, okay, so this whole equation over here is also equal to EI d squared y over dx squared. So what we have just done down here, we have just applied the elastic curve theory. Is that simple? Okay, you guys are like, is that it? Yeah, that's it. Okay, then from here, so this is my equation 2b. Then we integrate equation. We're going to integrate equation 2b. Okay, so EI dy by dx is equal to minus omega naught x4 over 24L plus by omega naught Lx squared over 12 plus by C3, okay, plus by C3, excuse me. So now this is our equation number 3, okay. So if we go back, can we solve for C3 now? The answer is no, because we don't know any of our slope, okay. What do I mean when I say we don't know any of slope? We know when this structure deform, okay, I'm going to draw in. Our structure will deform this way, right? We know. We don't know this angle, okay? So let's say at this point down here, we don't know what is this angle. And at over here, we also don't know. Sorry, that is not drawn in a right way. I do apologize. The first theta is wrong. We don't know this theta over here, okay? And then on the other side, we don't know what is the theta over here. We don't know all the slope, okay? So whatever we don't know, that cannot be used as a boundary condition, okay? So coming back to where we are, I hate Microsoft for doing this to me. Sorry, people. You can see what it's doing, right? It's rearranging my equation. And I don't know why. Hold on. 1, 2, 3, 4, 5, 6. Sorry. Okay, it's better now. It got unrearranged, I think. Yeah, it's better. So okay, I'll draw. No, it did something stupid for me again. Okay, now it's better now. I don't know. So why we don't know, I'll draw down here, right? So we know that this is our point A. This is our point B, right? And then this is our deflection. Okay, so this is our deflection. Right? We don't know what is this angle theta over here. Right? We also don't know what is our theta over there. Okay, at any point we don't know the theta. We don't know at all. Okay, so forget it. Okay, so don't. But we know one thing very interesting is this: when theta is equal to what? 0, y, the deflection y, right? The deflection y is at y max. Very interesting, yeah. Right, mathematically, right? That's why math is a language. I've been highlighting that to you for a few times now. So from here, we move on. We integrate again. We integrate EI y is equal to minus omega naught x5 over 120L plus by omega naught L x cubed over 36 plus by C3x plus by C4. Okay. So this is my equation number 4. So now we have our two boundary conditions, right? So we can substitute when x is equal to 0, right? Oh, you guys cannot see now. Right, we can substitute our boundary condition. X equal to 0. Y is also equal to wait, is one node crash again and it comes back. I wonder, is it my computer or the. So what I'm trying to do down here is I'm trying to turn on one node twice, one on the display screen, one on my writing pad, and it's always kicking me out. Okay, but anyway, it's easier for you to view. It's okay. It gone out again. Hold on. I had this same problem. You guys were with me. Some of you were with me on the Thursday night class. Same thing happened. Okay, I'll try it again. So now right? Y is equal to 0. And we're going to substitute into equation number 4. So therefore, we get C4 is equal to 0.